If there's a hurricane, Bob doesn't evacuate, he stays and measures valuable data about the violent surface currents. Thanks, Bob. Bob can help in all kinds of emergencies, including when a pollutant is released into the water. Bob drifts with the yucky stuff in the ocean currents and sends his data to be fed into computer models that help scientists predict its fate. Not only that, but if somebody gets lost at sea, who can help figure out where the ocean currents may take him? Bob can!
Hello everyone, and welcome back after lunch. If you could get seated, that'd be great. My name is Cecilia Maritsen, and I'm from the GoMRI Research Board, and I'm here to introduce Tamay Özgökmen. But before that, I would like to tell you about the movie we just saw, because that is a video clip from the award-winning movie Bob the Drifter, which has been mentioned several times. And that movie was made by the Carthay Consortium to explain science to elementary students. And I think we can all give an applause to Carthay for that little video. And the man behind Carthay, if I may say so, is Tamay. Tamay was one of the inventors of that drifter, and we could all be very proud that that's a biodegradable drifter. It's patented, and it can be used by everyone. It is used by a lot of people around the world already. I guess it's not so strange then that his PhD is in mechanical engineering. He is an engineer in his mind. He develops things, but he's also an excellent physical oceanographer. And he's very, very used to organizing complex interdisciplinary research projects. So in the aftermath of the Deepwater Horizon spill in 2010, he assembled here's a tongue twister. So this is Carthay. Consortium of Advanced Research on Hydrocarbon Transport in the Ocean, which was funded, which is good, by GoMRI to conduct multi-platform expeditions in the Gulf of Mexico, laboratory experiments and leading-edge computations, resulting already in over 200 publications and a lot of PhDs at institutions across the United States. I will also add that he is a great team player. He has been a go-to person for GoMRI for many years, and now in the last years where we've been doing the synthesis, he's been very, very, very helpful to us. So without much further ado, as they say, the floor is yours, Tamay.
Thank you, Cecilia, for this very kind introduction. And it's an honor for me to be here to summarize some of the results that were obtained literally by hundreds of students and researchers and other scientists. So I'm not really, this is not my thing. I'm representing dozens and dozens of people's research for over 9 years. So we focused on the physical aspects that are influencing transport of oil for this very peculiar problem. If you remember, the oil came from the bottom of the ocean, approximately 1,500 meters depth, 1 mile, from a very small pipe, this wide. Okay, it was two-phase flow coming with 1 meter per second velocity. So this is really a very peculiar situation for 3 months. And it made a big mess. So it's kind of mind-boggling to think that pipe flow can make such a big problem. That turned out to be physically and in all kinds of ways in science to be very, very rich. It lasted long enough to be influenced by the Earth's rotation. Then it hit the interface between the two largest reservoirs on the planet, which is the ocean and the atmosphere, which is a moving interface, and the breaking waves and all that stuff. So that was a very hard problem for us for years and years. It was influenced by hurricanes. There was a hurricane during the oil spill. And then, of course, the major socio-economic impact is when the oil hits land. And it turned out to be this was also a very rich problem because this area is dominated by a lot of freshwater outflows. And I'm happy to say that we looked at most, if not all, of these problems over the last 10 years. And the way we looked at these problems was actually by developing new observation systems. CART was initially a modeling project in the first funded phase, but we quickly realized we need a lot of data. And we became, 6 months into it, heavily observational, and the second phase and the third phase were very, very heavily observational. In particular, this was mentioned several times, we developed biodegradable drifters. This is not my invention. There were a lot of people in this room even who contributed to that. Excellent team. And deployed thousands of these in the Gulf to track the motion of the currents. And then we had also realizing the importance of, the problem is very interesting. You have they're at the surface of the ocean, which made it very, very easy to observe things from air. Initially, we went with a ship, and then we quickly realized, hey, we need to have balloons and planes and drones and all kinds of other instruments because this oil is at the surface of the ocean. So we developed very high resolution SST so that we can have our own plane and go underneath the clouds. We experimented with aerostat. It's a big balloon with a camera on it, and we attached it to a ship and then observed the motion at the surface longer than we could observe from planes. And we also expanded the use of a marine radar and developed a very specific marine radar so that we can see the currents around the ship in real time and in high resolution. That's kind of, you don't know what's going on around the ship usually in terms of the velocity field. And the result of these things are shown, summarized here. This is an experiment, it's a typical CART experiment where we are at the mouth of the Mississippi River flow. This is the area where we launch hundreds of drifters, and then we go into the small rectangle here where we have high resolution SST from aircraft, and then we go into the circle here where we have high resolution velocity field from the ship, and then we go into this little dot here where we have drift card measurements that we can observe from drones and aerostats. So in this way, we were able to see 100 times zoom in, telescope in, see the small picture, medium, and the large scale flow all at the same time. Not different days, different places, but all at the same time. That was the idea of the experiments. And then the large scale perspective was revealed by releasing approximately 2,200 of our drifters in different years and seasons in the Gulf of Mexico, northern Gulf of Mexico. All deployments were made over the Deepwater Horizon location. This is the concentration map from this paper of the Deepwater Horizon oil spill. And our first experiment, which was called GLAD, Grand Lagrangian Deployment, was exactly 2 years after the spill, and it showed a very good agreement with what happened during the spill. But then if you go in a different year or different season, this is a different season, which was an El Nino winter time, most of the drifters really went to Mexican continental shelf in a month. So you can expect some variability here. This was modeled. Once we have the data, then we could actually see if the models are working or not working, or what are the errors. This is a state-of-the-art fully coupled air, wave, and sea model from Shui Chan's group. And having the data, we could actually quantify, for instance, what's the spill area, how does it vary, how much beaching occurs, what's the transport out of the Gulf of Mexico. And we could correlate it with the northward extension of the loop current. If the loop current is far too north, then it creates a big spill. If the loop current is south, it creates a smaller spill for the northern Mexico. It's intuitive. But what we showed is how much the loop current varied in 2 years, okay? 2015, 2016, it's all different, okay? And this is sustained observations that we were able to carry out through 9 years of this program. Is the large-scale picture adequate? Probably one of the major accomplishments of this project was to show that actually small scales matter a lot. They matter in terms of the initial spreading of the plume. The modeling showed initially that the spreading of the plume was much slower than we have seen in reality, and this was confirmed in our experiments. And we could, unlike the oil spill that you see just the images, we could actually quantify it very, very accurately through these drifter releases and quantify the error in models. So if you have models that do not resolve all the scales of motion, and then you go and make an experiment and say, hey, this is what's happening at these small scales. These are kilometers, hundreds of meters, tens of kilometers. You don't capture the spreading of the oil, which is perhaps the most important period in the early stages of the development. And once you know the error, then the models can correct. If you don't know the error, if you don't know what's the reality, you cannot fix it. And we also saw a very good example of that during Hercules oil spill. This was, as Maggie said, this was a collective thing that came out. Mandy led the way, and we actually came together within almost half a day. And then students with drifters, our contribution was to send students with drifters. They were deployed around the Hercules spill. And what happened, so this is to track, spreading from that source. And what we saw over the next week is this significant stretching of the spill towards the south by a loop current eddy, which was not sampled by satellites because it fell in between the satellite tracks, because in Gulf of Mexico, the satellite tracks are sometimes there, sometimes not there, sometimes one satellite breaks, and so on and so forth. So there was no way for models to reproduce that because they did not have the right data coming from satellites. So we learned what's really, really important is local real-time data. It's not running some global model that gives you a solution. You need to have the solution that's in real time, giving you real information for that spill. And spills are very convenient for that kind of sampling because they're localized. You don't have to fill the entire globe with drifters. You can just dump over these things. And it gives you with 10, 50, 20 drifters, very inexpensive fashion. We can deploy them from air now. Good information. And this, I think, is a template for response to the state. If you have an oil spill, you deploy these drifters, go there, and assimilate into ocean models and get a very good forecast, no matter it's hurricanes, bad weather, night, so on and so forth. Okay, it doesn't cost a couple $1,000s, really. The drifters are inexpensive. Our drifters are about 10 times more cheaper. So we wanted to have not the Rolls-Royce, but we want to have Ford Model T that you can make it available to the community. It's cheap. You don't worry about it. A glider costs $1 million. This drifter costs $200. Okay? So that was one of the things that we wanted to leverage. Another important thing that we found again and again and again, and this is to our surprise, is how freshwater fronts that are dominating the entire region, northern Gulf of Mexico, affect transport near the coast. And this is an image. We were making an experiment, dropping our drifters, and drifters were behaving in ways we couldn't understand. And then Hans Graeber had the SAR, synthetic aperture radar image with 1 meter resolution, and we overlaid after the experiment. And to our surprise, all our drifters were actually coinciding with freshwater fronts. I mean, and they are 1 meter wide. They're not 1 kilometer, 1 meter. And then in the next, we did quite a bit of work on it. In particular, one of the most important things we did was with Willy Krofulu's group, where we actually determined that the pathways of the Taylor oil spill. Taylor oil spill, Deepwater Horizon oil spill is the largest accidental oil spill. Taylor oil spill is the longest oil spill. It's been going on for 14 years. And by deploying drifters, we show that oil spills do not take the shortest path to the coast. They are entirely blocked by freshwater fronts, and therefore they take these long ways, kind of delineated by the freshwater flows or into the interior of the Gulf of Mexico. And after this work and a couple other papers, I think Coast Guard understood this issue. There were a lot of people contributed to that, and now it's shut off. So this is probably the most important accomplishment of the physical group, that they contributed to shutting off the longest oil spill in the Gulf of Mexico. Another joint work with Helena Gabriel's group showed similar things. Her group was looking at chemical concentration from the sand, and were able to show that actually the freshwater plumes that are kind of emitted from the coastline control when Deepwater Horizon oil landed on the sand. And this is a nice work. They're all published. And this is an extreme example when we released 300 drifters over an area the size of a large city okay, much larger than Tampa. And this is a case where if you have a lot of resolution, you can see much more. If you have few drifters, you don't see that. With 300 drifters, we found that after 1 week, most of them collapsed on the size of this room. So there was a sinkhole that you can only capture if you have a lot of data points. If you don't see a coarse grain, you don't see that. Yet it sucks all the material, the size of Tampa, onto this room and sends it down with huge vertical velocities. So this was essentially, the area contraction was 1 million times. And it was published in PNAS immediately because it was a frontier. It's the first time this was observed. So people thought, oh, wow, the ocean has these kinds of things, kind of situation. Now, I like to think we contribute a lot to data assimilation in numerical models with the leadership of Greg Jacobs, good friend of mine. We've been working together for 10 years at NRL. And they were able to show with many papers that assimilating drifter data is quite effective tool for mapping out the features in the ocean and transforming them communicating them into the ocean models. But more important thing, I think, that it is the finding or the admission, or I would say determination in Greg Jacobs' very recent paper, in that ocean modelers for years and years, they've been running higher and higher and higher and higher resolution models to the extent that it gets longer and longer and longer to analyze this output. And the models have all kinds of creatures in them and so on and so forth. But the models just generate a solution space, actually. They can generate essentially infinite number of solutions for a given initial condition, boundary condition. Just now, that's the nature of the Navier-Stokes equations. And Greg showed unless you constrain these solutions by actual data, these added fine features are not really add-on, but actually it can make the solution worse. So high-resolution modeling definitely requires high-resolution data to be realistic, okay? Unless you are exploring the model or physics, it's fine. It's a physically correct solution. But if you are in a response situation, you are not going to have a huge model running 100 times. You are overwhelmed with the solutions. None of them could be realistic, in the sense that that's not what's happening out there in the ocean. So less is more, and I think there's a course correction that's coming up with this in the modeling community. Okay, oh, sorry, this is the wrong button. Now, I've been working in turbulence for a long time, I guess now. And one of my favorite papers is the Richardson's 1926 paper. So turbulence thing has not been really advanced all that much, even though there are literally millions of papers. But in this paper, Richardson makes a very good observation by looking at 3-4 smoke stacks in England and derives a turbulence dispersion relationship, which has been always valid and one of the most important papers in turbulence, real turbulence, not oceanic turbulence. And we wanted to see if this law applied to the oceanic turbulence. And because we have all these data sets from drifters and cards and planes and so on and so forth, we could patch all these data sets and see if this law remains valid. So what we found is that this law remains valid with, amazingly, okay, over 5 orders of magnitude in scale range, with 2 exceptions. One is the surface of the ocean, where you have very weird situation, wind, high wind, waves, and all that stuff. And the dispersion actually is enhanced by 10 times. And the other one is the hurricane. And as you have seen in the movie, we had a situation where we released the drifters, and after 2 weeks, a huge hurricane passed over the drifters, and drifters actually did not break. I mean, some broke, but most of them transmitted data, so we could study how the ocean dispersion happens under hurricanes. And under hurricanes, not surprisingly, you get another factor of 10 or so high dispersion. So since near the surface the dispersion is enhanced, the question is becoming, how deep is that happening? What's the profile? Because most of the oil is concentrated in the upper, or most of the oil that you can respond to in terms of response efforts, okay, is in the upper few centimeters, few inches. You cannot do much about the depth and so on and so forth. So that's a special area of interest for us. And this experiment was completely designed by a PhD student. He attended our first experiment in 2012, and he was like watching. And then in 2017, when we were at the ship, he said, how about we try that? Okay, after 5 years, he designed this experiment in an hour, literally, and we did it because we had a lot of time. And he combined AUV, drifters, drones, and a lot of stuff that's mounted at the front of the ship that I don't have time to get into. And by overlapping all these things, we could actually come all the way to 1 centimeter close to the surface of the ocean. I mean, if you try to measure the currents with a huge device the size of me or bigger, you're not going to get 1 centimeter. You're going to get a couple meters. To get to 1 centimeter on a moving interface is kind of an accomplishment. And this was also published. And the main finding is that the currents at the surface are 4 times larger than what people used to consider surface before GoMRI, which is 10 meters. Okay, because it was like ocean models, 10 meters, that's kind of close to surface. It's not surprising that it's larger, but we were able to quantify that. And these techniques can be used to look at it any other place. And this has implications for landfall, because we showed in another paper that actually by accounting drifters that account more for the Stokes drift waves, you get a better agreement with what happened during the Deepwater Horizon spill. Okay, I always press them. So coming to the Plume part, I have just a few slides on that. This is the first image of Deepwater Horizon that I saw. It was my birthday, and then I opened New York Times, and this was the picture. And I immediately thought, I've been teaching GFD, geophysical fluid dynamics, for a long time, and this thing screams at you that it's actually the plume that's driving the ocean rather than the ocean is driving. So the plume is actually creating flows, okay, on its own. It cannot be just passively advected by the ocean currents, but you have to account for the effect of the plume on the ocean currents. That's kind of adverse thinking. It took us a lot of time to convince people on that, but there was some good work done on it. We did it in 2 ways. We created a fancy plume model, multi-phase gas and oil, which was confirmed by laboratory experiments, and showed that if you put rotation on it, Earth's rotation, it makes this precession, it starts spinning around like a child's toy top, okay? And then the people at the Cambridge University in England, they also like this idea, they're part of our group, and they did laboratory experiments. They actually designed a special tank for it, and they were able to make it very, very simple. They relate the precession rate of the plume to the Earth's rotation in this very simple formula. It's like half the Earth's rotation. So if the plume lasts more than a few days, if the oil spill lasts more than a few days, you get this in all cases. Another line of research that was initiated by another picture. So pictures are very, very powerful. And this caught my attention together with Michel Boufadel. This is an ADCP section of the real Deepwater Horizon, published in a kind of obscure method that I had to dig out. But it immediately caught my attention in that you had this like a patchy picture of the Deepwater Horizon. And then we start digging into what exactly happens in two-phase flows. And two-phase flows actually have multiple shapes. Okay, you can have a completely mixed two-phase flow, gas and oil mixed completely, no gaps. Or you can have like a Swiss cheese situation where you have these huge gaps of gas, and then you have oil, gaps and oil, and so on and so forth. And then we were able to show that actually there is high likelihood that the Deepwater Horizon spill was in this Swiss cheese regime of gas and oil that are kind of separate from one another. In this case, you have to consider that you're going to make changes in your outflow rate that are estimated, as well as the bubble size, the droplet size distribution, which is a major parameter in these studies. And then this brought us immediately to OMSET, because we realized we cannot really model these things very, very easily. We were doing modeling until that time. Even in the lab, Cambridge lab, we were using a nozzle of 1 millimeter. Okay, this is compared to half a meter real thing. So you are not going to do half a meter. And we were able to do 2 major experiments. Some of the people who ran these experiments are in the room at OMSET tank in the summer of 2018 and 2019. And the way we observed the churn flow coming from this pipe was through developing what we call a shadow graph. camera that through which we can actually, this you can use in the tank, you can use in the field. It's a very flexible device, again developed at Erasmus, University of Miami, where we can see the distribution of the droplets, and this becomes an input to your empirical model down the line. So this is very much ongoing work. It's not finished, but I think it's very, very exciting what Michel is doing. So I would like to provide some broader impacts. Just 1 minute. So GoMRI supported all these observations, modeling, and research. And of course, oil spills happen. Big oil spills like this happen maybe every 30 years. Hopefully never again. But 30 years is kind of a typical frequency. But I think this kind of knowledge and expertise is applicable to other pressing issues, such as plastics in the ocean. This is like a permanent oil spill because plastics, unlike oil, last 1,000 years in the ocean. Spreading of red tides, this was a major problem in Florida last year. Sargassum's problem, that's a huge problem in Caribbean. All kind of same understanding. Even the climate problem, because we are finding these frontal zones that we discovered in the ocean are the primary ways that the ocean and atmosphere interact in a large scale. I think we improved modeling at NRL group. I feel good about that. We invested heavily because I knew that once GoMRI funding ends, NRL will go on. So this is a legacy issue for us. It's not like we could close the shop, but all the knowledge transferred will stay in that group. They operate for decades and decades. For the I'll skip that because I think, yeah. Jet Propulsion Lab, this is another legacy issue. Attended 2 of our experiments. They tested 2 devices. One was altimeter, high-resolution altimeter, which didn't work all that well. They admitted that. And then they developed another instrument called Doppler scat. This is very similar to what we were doing with the drones and radar. It's just you can do it from space. And this now created a huge program. They are going to start experimenting on that next year. And in 5 years, hopefully, it will go on space. And I think David knows more about that than me. DARPA, Defense Advanced Research Project Agency, they liked these massive distributed floats because they realized that they can actually use that for military reconnaissance by putting a lot of sensors, not one sensor, not just the location, but multiple sensors, up to 710. And they are aiming at 50K. Okay, we did 2K and they want to do 50K. And actually, they kind of continuing what we started here in the Gulf. The major experiment started last week. The data is coming, and they are intending to come back to the Gulf and sampling it, hopefully, with a lot of data points. ONR used to rely a lot on very expensive instruments like gliders, and now they see that you can generate much more real-time data using these cheap instruments that we developed. And in the recent experiments, they've been using at least 300 of our drifters just to see what's going on, where to sample, and so on and so forth, instead of relying on satellite, which is once a day or sometimes never during experiments. And finally, one of the outcomes that I did not at all expect from this efforts of our observational program, because for years and years I was pushing the program to get more and more and more and more data because we want to know more about what's going on. All of a sudden we ended up with too much data. And to the extent that the students do not have the time during their PhDs, 5 years or something like that, to analyze it. And then this is expensive data. This is the ship time, aircraft time, and so on and so forth. You just cannot forget about that. So I'm very, very happy that GridC is going to be around for 10 more years. But this data needs to be analyzed. And if people go the same path, generating a lot of data from different kinds of instruments, then you really need to find a way to analyze the data faster than what we do now, because oceanic data have been few. And with that in mind, this essentially Department of Defense has a new machine learning project in which the idea is how can we identify what's interesting in the data and in fact even make forecasts based on just data alone, not modeling, but just data alone, just like the stock market. And this just started, and it's a very exciting project. So finally, I would like to use this opportunity to thank the board for everybody who was involved in the physical aspects. It was very generous. As David says, it was real money. And the project was really a dream project for me. And it was very purposeful. The focus was sharp. Everybody could realize what they were dealing with. You know, it was like moon mission. You put a flag on the moon and return, come back. You can say it in one sentence. It's very important. Otherwise, everybody does something else. Scientific content turned out to be like a fractal. It's more and more and more. The more it supported thousands of people for 10 years, and we feel that we didn't do enough. And it's hard to find a problem like that. It was flexible in the sense that we could actually we had a lot of flexibility. It was not like GoMRI was dictating us what to do. We had huge collaborations, okay? We had 20 institutions at CART, and it was never the case. If you have one collaborator, you're lucky. We are talking about 100 people from 20 institutions. It had also applied nature, okay? It was not just basic science, some esoteric calculating the 100th digit of pi or something. It was very applied. Duration was long enough that we could actually finish something. And it was very intense. GoMRI, you know, competitions every 3 years. You don't get, they didn't leave us, okay, here it is, see you later in 10 years. So thank you very, very much.
Thank you, Tamay. That was a wonderful lecture. Very, very nicely done. We have two questions on cards, and if there are additional cards, somebody can bring them up, but I'll start with one of the cards. Tamay, one slide said, local data is better than remote data. It's not for me. Please tell us more. Does this suggest we should reallocate resources to support local data collection?
For this problem, for the oil spill problem, okay, you know where the oil spill is, and you want to go there and deploy everything. That's maybe done, okay? But it's not like, I mean, the idea that you have some model configured and it's going to tell you what's going to go to what's going to happen in the oil spill in anywhere, and that's not. I have objections to that. So you need real data on top of the oil spill. It's not expensive.
Thank you. One more question is, or comment. Based on what you have learned about freshwater fronts, would you recommend oil spill responders use increased freshwater outflows as a way to keep oil out of wetlands and other coastal habitats?
Yes.
Thank you for thank you. If there are no other questions, as a moderator of the Q&A, I think I'd like to ask a question then. Tamay, GoMRI was a fortunate source of funds for the work you described. How would you suggest that some type of sustained observing system be maintained in anticipation of the many applications of the data that you described?
Okay, so I'm of course not as familiar as you are with all, you know, what's going on in the United States about funding and all that stuff. But two things I see very promising at kind of our end is this Jet Propulsion Lab really took this initiative, and I think this Doppler SCAT program will be successful because there are very, very good people working on it. It was already successful during our tries, and it's going to be going to the satellite, and that's definitely one way of providing sustained information. The second thing that we started working with the Carnival cruise lines. These are essentially ships of opportunity, and they are very, very interested in generating kind of free data. And if this, for instance, we are going to have a cruise in a few months where we are going to give them essentially our drifters, and in the future, if they generate, let's say, with expand radar, velocity field around them, and they have a lot of ships going back and forth, that's an inexpensive way of generating constant data, and if this can be uploaded to some real-time server, wherever the ships are, and they are kind of all over the place. And the third one is, of course, NOAA they do routine observations. We don't do routine observations, we do what's new. We cannot get funded to do what's routine. And maybe there are others, but you know more about that.
No, thank you. I'd like your suggestion about future is based on ships and satellites and oceanography, SOS, if you reverse the things. Thank you very much, Tamay, and let's give another round of applause.
Thank you, thank you. It's an honor to be here.